In the vast theater of the cosmos, every story we have told about our origins begins with a singular moment, a birth. For over a century, the prevailing narrative has centered on a cataclysmic event, the Big Bang, a single point of unfathomable density erupting into space and time itself, expanding and cooling, giving rise to galaxies, stars, planets, and eventually to us. It is a story so entrenched in modern cosmology that it has almost become an article of faith, a foundation upon which the rest of astrophysics is built. But what if that foundation is not the only one possible? What if the universe, in all its endless sprawl, had no beginning at all? The question is as radical as it is ancient. For thousands of years, philosophers, theologians, and scientists have struggled with the idea of eternity. An eternal universe means there was no first cause, no initial spark, no cosmic birth. Instead, it suggests a reality that has always been here, stretching infinitely into the past as it does into the future. To contemplate such a universe is to challenge our most intuitive grasp of existence, because we humans are creatures who begin and end. We are born, we live, we die. Everything we know seems to have a start. To imagine something without one is to step beyond the boundaries of ordinary thought. In the mid-20th century, as the Big Bang theory began to dominate scientific discourse, an alternative idea emerged, the steady-state theory. Developed and championed by astronomers Hermann Bondi, Thomas Gold, and Fred Hoyle, the steady-state model proposed that the universe, while expanding, remained essentially unchanged in its overall appearance. New matter, they argued, was continuously created to fill the gaps left by expansion, keeping the density of the universe constant through time. In such a cosmos, galaxies would form and drift apart, stars would be born and die, but the large-scale structure would remain eternal and unaltered. No beginning, no end, only an unbroken continuity. For Hoyle, who famously coined the term Big Bang as a dismissive jab at the rival theory, the steady-state universe was a deeply appealing vision. It avoided the troubling question of creation, a problem that straddled science and theology uncomfortably. If the universe had a beginning, then what or who set it in motion? An eternal cosmos required no such leap. It was self-sustaining, forever renewing itself in an elegant cycle. In Hoyle's view, science did not need to grapple with metaphysics. The universe itself was explanation enough. At first, the steady-state model was not without its supporters. Observations of galaxies and quasars were still in their infancy. The evidence for the Big Bang was suggestive, but not yet overwhelming. The idea that new hydrogen atoms could spontaneously appear in the void of space might have seemed strange, but not impossible. After all, quantum mechanics had already shown that particles could emerge seemingly from nothing, fluctuating in and out of existence in the quantum vacuum. Why not on a cosmic scale? But as telescopes improved and data accumulated, cracks began to appear. Astronomers found that distant galaxies looked different from nearby ones. They were younger, more chaotic, less evolved. This implied that the universe was not the same everywhere through time, but rather that it had a history. Then came the decisive blow, the discovery of the cosmic microwave background radiation in 1965, the faint afterglow of a hot, dense beginning. This relic radiation fit perfectly with the Big Bang model and could not be explained by the steady-state theory. One by one, the pillars of the eternal universe crumbled, and the Big Bang emerged victorious. Yet, the allure of a cosmos without a beginning never truly vanished. Even as the Big Bang became the dominant paradigm, cosmologists continued to wrestle with the question, what happened at time zero? The equations of general relativity describe a universe that contracts backwards in time to a singularity, a point of infinite density where the laws of physics break down. But such a singularity is not truly an explanation. It is a boundary, a limit beyond which our current understanding cannot go. For many scientists, the notion that time itself simply began 13.8 billion years ago is as philosophically troubling as it is scientifically incomplete. And so, the door remains open, ever so slightly, to the possibility that the universe had no beginning. Some modern theories attempt to resurrect the spirit of the steady state in new forms. Perhaps the universe undergoes endless cycles of expansion and contraction, the so-called Big Bounce, with no first cycle, only an infinite chain stretching into eternity. Or perhaps our cosmos is just one bubble in an eternal multiverse, where universes constantly bud off from each other, creating a steady-state-like backdrop of perpetual creation. Even the mysterious phenomenon of cosmic inflation, the rapid exponential expansion thought to have occurred in the earliest fraction of a second, has versions that imply inflation itself could be eternal, endlessly spawning new universes in a grand cosmic froth. To ask whether the universe has no beginning is not to cling nostalgically to a discarded theory, but to probe the deepest boundaries of cosmology. It is to confront the possibility that our quest for origins may never find a single sharp answer. Instead, we may discover that the universe, in its grandest sense, is not a story with a first page, but an endless book without cover or spine, its chapters unfolding without origin or conclusion. Imagine standing beneath the night sky, the stars scattered like grains of fire across the darkness. We are told this panorama had a beginning, a first light emerging from primordial darkness. But what if that darkness never truly ended and never began? What if the stars above are but one moment in an eternal cycle, their birth and death part of an infinite rhythm that has always played and will always play? In such a vision, the universe is not a fleeting firework, but an endless flame. As we venture deeper into the cosmos with our instruments, as we peer farther back in time with each new telescope, we may find answers that affirm or challenge our most cherished theories. But for now, the question remains, did the universe truly have a beginning, or has it always been here, steady, eternal, waiting for us to notice? And it is here, with this haunting possibility, that our journey truly begins, exploring not only the evidence for the Big Bang, but also the scientific, historical, and philosophical landscape that still entertains the idea of a cosmos without birth. Because to challenge the beginning is to challenge everything we think we know about existence itself. The human mind is not well equipped to think in infinities. We evolved to survive days and seasons, to measure life in years, perhaps decades. Our stories begin with once upon a time and end with conclusions. But cosmology, in its most daring speculations, asks us to stretch beyond this framework. To imagine a universe with no beginning is to stare into a chasm where time itself loses its footing, where there is no once and no upon a time, but only an unbroken expanse of existence. And that kind of thought resists the boundaries of language itself. To truly grasp what a steady or eternal universe would mean, we need to revisit the turbulent mid-20th century, when the very nature of cosmic origins was an open battlefield of ideas. At the heart of this struggle stood Fred Hoyle, a brilliant, sharp-witted astrophysicist with an aversion to beginnings. Hoyle, along with Thomas Gold and Hermann Bondi, felt that a universe with a finite age posed a dangerous philosophical trap. If the cosmos had a beginning, then what preceded it? To Hoyle, this was an illogical question, one that could too easily be hijacked by theology and metaphysics. By contrast, an eternal universe neatly sidestepped such ambiguity. The cosmos simply was, with no need for supernatural intervention or impossible causation. The steady-state theory they proposed was, at first glance, both radical and elegant. If galaxies are receding from one another in an expanding universe, then the density of matter should gradually thin out. But Hoyle and his colleagues proposed a solution. What if new matter were constantly created from the vacuum, atom by atom, at just the right rate to maintain cosmic balance? By their calculation, only a few hydrogen atoms would need to appear per cubic kilometer of space each year, so little that it would evade detection, yet enough to replenish the universe forever. Stars would condense from these atoms, galaxies would form, expand outward, and eventually fade from view. But on the largest scale, the universe would look the same in every direction and at every epoch, eternal, unchanging, without a birth and without an end. This vision was not just science, but almost poetry, a cosmic machine that renews itself perpetually, erasing the need for a singular genesis. It drew supporters who were uneasy with the philosophical implications of the Big Bang. For some, steady state even carried a kind of comfort, suggesting that the universe was stable, not headed toward a final collapse or heat death. The cosmos, in this model, was less like a fragile firework and more like a ceaseless ocean, waves rising and falling, but the sea itself eternal. But science is not built on philosophical preference. The beauty of a theory is secondary to the evidence it must face. And in the 1950s and 1960s, evidence began to accumulate that placed steady state under strain. Astronomers peered deeper into space and further back in time, and what they saw did not align with Hoyle's eternal vision. Distant galaxies appeared younger, more primitive, filled with furious bursts of star formation. If the universe truly looked the same in all epochs, then galaxies billions of light-years away should resemble our neighbors today, but they did not. The past looked different from the present. More troubling still were discoveries of strange, powerful objects at the edges of observation, quasars. These quasi-stellar radio sources blazed with the energy of 1 trillion stars, yet they appeared faint and tiny, implying that they were enormously distant. And if they were distant, they were also ancient, belonging to a young universe. Their scarcity nearby suggested they were relics of an earlier era, an unmistakable sign of cosmic evolution. Quasars were nails in the coffin of steady state. And then came the death blow, the discovery of the cosmic microwave background. In 1965, Arno Penzias and Robert Wilson stumbled upon a faint, pervasive radio signal that filled the sky in every direction. It was a whisper from the early universe, the cooled remnant of once fiery origin. The Big Bang had predicted such a background as the afterglow of creation itself. Steady state could not account for it. In a single stroke, decades of argument tilted decisively toward a universe with a beginning. Hoyle resisted fiercely, never conceding defeat. He refined his theory, proposing complex alternatives like the quasi-steady state model, where many creation events dotted cosmic history. But the tide of evidence was relentless, and most cosmologists abandoned the eternal universe. The Big Bang reigned, and still reigns, as the standard model of cosmology. And yet, questions remained. The Big Bang describes the expansion of the cosmos from a hot, dense state 13.8 billion years ago, but it does not explain what preceded it. Was there truly a singularity, a moment where physics itself dissolved? Did time simply switch on, like a lamp in the void? Or is the Big Bang less an absolute beginning than a transition, one phase in a deeper, perhaps eternal process? Even today, Some of the most ambitious theories in cosmology echo Hoyle's yearning for eternity, though they cloak themselves in modern mathematics and quantum physics. The idea of cosmic inflation, the blistering expansion thought to have occurred a fraction of a second after the Big Bang, has variants where inflation is eternal, endlessly spawning new regions of space-time, each with its own Big Bang. In such a framework, our universe may be one bubble among countless others, each born from a steady background of creation. The multiverse, if it exists, is eerily reminiscent of steady-state's continuous renewal. Other theories propose oscillations, universes that expand, collapse, and bounce back again, with no first cycle and no final end. Or perhaps quantum gravity itself eliminates the singularity, smoothing out time so that the universe stretches infinitely into the past. In these modern visions, the steady state is reborn, not as a literal creation of atoms, but as an eternal backdrop of processes that prevent the universe from ever truly beginning. And so we stand at a crossroads of imagination and evidence. The Big Bang tells us much about how the universe evolved, but little about why it exists at all. The steady state, though discarded, still haunts cosmology as a provocative alternative, a reminder that beginnings are not the only possible story. To question the beginning of time is to confront one of the deepest mysteries of all. Why is there something rather than nothing? And perhaps, if the universe is eternal, the answer is simpler than we think. There was never nothing. There was always something, and always will be. As we push our gaze further into the cosmos with new instruments, giant telescopes, gravitational wave detectors, and satellites that can read the faintest afterglow of creation, the lines between beginning and eternity may blur once more. What we discover could force us to rewrite the story of everything. To imagine a universe without a beginning is to challenge not only physics, but the very way we think about existence. A cosmos without a starting point seems to stretch infinitely backward, with no first instant, no origin event to mark the birth of reality. This is not just a scientific puzzle, but a profound philosophical riddle, one that has haunted human thought for millennia. The ancient Greeks wrestled with it, debating whether time itself could be infinite. In Hindu cosmology, cycles of creation and destruction spanned eons, with no true beginning or end. Even medieval scholars argued fiercely over whether the cosmos was eternal or divinely created in a moment. And now, in the modern age of telescopes and particle accelerators, the question returns with new urgency. The Big Bang Theory gives us a powerful narrative of cosmic history, tracing the universe back to 13.8 billion years ago, when all known matter and energy were compressed into an unimaginably dense state. From that fiery origin, space itself began to expand, cooling and giving rise to galaxies, stars, and planets. The evidence is strong. The cosmic microwave background radiation, the abundance of light elements like helium and deuterium, the redshifting of distant galaxies as space stretches outward. Yet even the Big Bang leaves us with a problem. It explains what happened after that initial moment, but not the moment itself. If time began then, what does before even mean? If time did not begin, then what is the true nature of eternity? Here, the steady-state theory takes on a different kind of importance, not merely as a scientific model, long since set aside by most cosmologists, but as a reminder that beginnings are not inevitable. Fred Hoyle's vision of a universe that constantly replenishes itself was not just a technical hypothesis, it was a philosophical stance against the notion of creation ex nihilo, creation from nothing. To Hoyle, nothingness was a meaningless concept. There was always something. If matter could emerge continuously in the fabric of space, then perhaps the question of origins could be dissolved, replaced by an eternal, self-sustaining cosmos. Modern physics has begun to flirt with similar ideas, though in far more intricate forms. Quantum field theory suggests that the vacuum of space is not truly empty, but a seething froth of energy and fluctuations where particles can pop in and out of existence. Could the entire universe itself be the product of such fluctuations not once, but continuously, without need for a first event? In some inflationary models, this idea takes on cosmic proportions. Space-time itself eternally inflates, endlessly budding off new pocket universes, like bubbles in an infinite foam. Our universe, then, may be only one among countless others, with no single beginning, but an endless process of creation. If this is true, then the Big Bang we see is local, not universal. It marks the birth of our cosmic region, but not the beginning of existence itself. What we call the universe might just be a small fragment of a much larger, perhaps eternal reality. This possibility challenges our human instinct to look for singular origins. It forces us to consider that the beginning might simply be an illusion, a parochial perspective from within one particular bubble of space-time. But let us pause and reflect on what eternity really means. Imagine walking backward in time, past the rise of humanity, past the extinction of dinosaurs, past the formation of Earth, past the birth of the sun, past the galaxies coalescing, past the first stars igniting from clouds of hydrogen and helium. Keep walking, further and further, past the cosmic microwave background, back into the first fractions of a second after the Big Bang. If the universe had no beginning, then this journey does not stop. There is no wall, no singular instant to reach. Time extends indefinitely backward. There was always a before, and always another before beyond that. This endless regression unsettles us because it clashes with causality. Every effect must have a cause, every event a prior trigger. But if there was no first event, then causality itself may be incomplete. Could it be that our concept of cause and effect is only a local feature of the universe, valid for finite stretches of time, but not for eternity? Some philosophers have suggested that the cosmos does not need a cause because it is, in itself, necessary. It simply exists as a brute fact, requiring no explanation. To some, this sounds unsatisfactory. To others, it is liberating. The stakes of this question extend far beyond abstract thought. If the universe had no beginning, then so did we in a chain of events that leads back to a single point. But if the universe has no beginning, then our origin is not truly an origin at all, but merely one moment in a ceaseless flow. We are not children of a singular birth, but participants in a process with no start and no end. Does this diminish our significance, or does it elevate us, making us part of something eternal? Consider again the night sky. Each star we see is already part of a cycle, forged from ancient clouds, burning for millions or billions of years, destined to collapse into white dwarfs, neutron stars, or black holes, only for their remnants to seed new stars. This cycle already hints at eternity, even within the finite age of our universe. Perhaps what Hoyle and others intuited was that this cycle has no ultimate beginning, that it simply continues backwards without limit. Of course, evidence matters, and today the observations overwhelmingly support a hot and dense origin. But science has always been shaped by bold questions, even those that resist immediate answers. To ask whether the universe has no beginning is not to deny what we know, but to probe deeper into what we do not know. It is to admit that our story of everything may still be incomplete, and that beyond the bright frontier of the Big Bang lies a mystery even greater, the mystery of eternity. And so the debate persists, not just in physics, but in philosophy, theology, and human imagination. Perhaps one day we will discover that the universe's beginning was only a beginning for us, not for reality itself. Perhaps eternity is the true stage upon which all cosmic dramas play. To understand how modern science approaches the question of a universe without a beginning, we must step into the strange and often counterintuitive world of theoretical physics. The Big Bang model tells us what happened after the universe was already hot and dense, but when we push backward, closer and closer to time zero, we eventually arrive at a wall, a singularity where our equations collapse, where density and temperature become infinite, and the laws of physics simply stop working. For many cosmologists, this abrupt stop is not an answer, but a challenge, a sign that the framework we rely on, Einstein's general relativity, cannot, on its own, explain the true origin of the cosmos. And so the search begins for theories that go deeper, that might show us what lies beyond the apparent beginning. One of the most compelling of these ideas is the notion of a cosmic bounce. Instead of a singular birth, the universe may have experienced a contraction before its current expansion. Picture space itself collapsing inward, galaxies rushing closer together, stars and planets obliterated in a crushing reversal, until matter and energy compressed into an almost inconceivable density. But rather than ending in a singularity, some new physics may have triggered a rebound, a bounce, that turned contraction into expansion. What we call the Big Bang may, in this picture, simply be the latest bounce in an infinite sequence of universes, each one born from the ashes of the last. This cyclic universe model has roots in both ancient philosophy and modern physics. The ancient Stoics believed in endless cycles of cosmic birth and destruction. In Hindu cosmology, time was measured in unimaginably vast cycles of creation and dissolution. In the 20th century, Richard Tolman, an American physicist, attempted to fuse Einstein's relativity with thermodynamics, proposing a universe that oscillates between expansion and collapse. The flaw in Tolman's version was entropy. With each cycle, disorder would accumulate, making future universes larger and longer-lived than past ones, ultimately pointing back to some first cycle. But newer theories, drawing on quantum mechanics, suggest ways around this problem. Perhaps entropy can be diluted during a bounce, resetting the cosmic clock and allowing cycles to stretch back forever. Another framework comes from string theory, with its higher dimensions and exotic geometries. In the ekpyrotic model, our universe could be a three-dimensional brane floating in a higher dimensional space. Collisions between such branes could trigger Big Bang-like events, not as one-time beginnings, but as recurring interactions in an eternal higher dimensional stage. In this vision, what we see as a cosmic birth is just a byproduct of larger dynamics we cannot yet directly observe. Our universe is one spark in a perpetual storm. Then there is the idea of eternal inflation. Inflation theory was originally developed to solve puzzles in the standard Big Bang model, such as why the universe appears so uniform and why space is so flat on large scales. It posits that in the first instant after the Big Bang, the universe underwent an exponential expansion, inflating faster than the speed of light for a tiny fraction of a second. This rapid stretching smoothed out irregularities and set the stage for the cosmic structures we see today. But when physicists studied inflation more closely, they realized it might not end everywhere at once. In some regions, inflation may stop, creating pocket universes like ours, while in other regions it continues endlessly. If so, inflation is eternal to the future, generating an infinite multiverse of universes, each one with its own properties and histories. But if inflation can be eternal forward in time, could it also be eternal backward? Could there have been no first moment, only an infinite past where universes are continually budding off from an inflating background? Some researchers argue yes, while others suggest that even eternal inflation cannot escape an initial beginning. The debate is fierce because it cuts to the heart of what physics can say about eternity. Quantum cosmology adds another layer to the puzzle. In the strange rules of quantum mechanics, particles can tunnel through barriers that would be impossible classically. Some physicists speculate that the universe itself could tunnel into existence, not from nothingness in the ordinary sense, but from a quantum vacuum state that has always existed. This is not nothingness, but a seething, timeless substrate of reality, full of potential. In this picture, the question, what happened before the Big Bang, dissolves, because before has no meaning in a timeless quantum realm. The Big Bang becomes not a beginning, but a transition, like a wave cresting on an eternal sea. All these ideas, the bounce, the cycles, the multiverse, the quantum vacuum, are attempts to grapple with the same unsettling fact. The Big Bang, as traditionally described, cannot be the whole story. Something must underlie it, whether it is another universe, another dimension, or an eternal background that defies our intuition. In this way, modern cosmology echoes the spirit of the steady-state theory, though in far richer and stranger forms. Hoyle imagined hydrogen atoms appearing spontaneously in empty space. Today, we imagine entire universes budding, bouncing, colliding, or tunneling into being. What unites all these scenarios is the rejection of a singular absolute beginning. Instead, they suggest continuity, cycles, or eternal processes. They imply that time does not emerge from nothing, but flows without end, that the universe is not a fragile one-off event, but part of a deeper fabric of reality. And yet, for all their elegance, these ideas remain speculative. Observations may one day discriminate between them, but for now, they are tantalizing possibilities, glimpses of a cosmos that may be far stranger than our current models allow. And here lies a profound tension: the human desire for origins against the possibility of eternity. We are storytellers by nature, and stories have beginnings. But what if the universe itself is not a story, but an endless poem with no first line and no final verse? To embrace that vision is to confront the infinite, and in doing so, to expand the very limits of what we mean by existence. As our instruments sharpen and our theories deepen, we inch closer to the truth, but with each discovery, the horizon recedes. The Big Bang might not be the beginning, but a doorway. Beyond it may lie other worlds, other epochs, perhaps an infinity of them. The steady state is gone as a formal theory, but its spirit lingers, transformed, reminding us that the universe may have always been and may always be. When we speak of eternity in the cosmos, we must ground our imaginations in evidence. Theories can dazzle, but the universe answers only through light, through signals that have traveled across billions of years to reach us. If the universe has no beginning, if it is eternal or cyclic, then there must be fingerprints, subtle traces left imprinted in the structure of space-time, in the radiation that bathes us, in the distribution of galaxies across the heavens. And so astronomers turn their instruments skyward, asking the sky itself whether it remembers. The most powerful clue we possess remains the cosmic microwave background radiation, the faint afterglow of the Big Bang, discovered in 1965. It is a near-uniform bath of microwaves that fills every corner of the sky, the relic light from when the universe was only 380,000 years old and atoms first formed, allowing photons to stream freely through space. For Big Bang cosmology, the CMB is a triumph, a snapshot of the infant cosmos that confirms a hot, dense origin. But it is also a challenge. If the universe is truly eternal, what does this relic mean? For many cosmologists, the CMB does not exclude eternity, but reframes it. In cyclic or bouncing models, each Big Bang would leave behind its own microwave afterglow, perhaps overwritten or altered by subsequent cycles. Tiny anomalies in the CMB, minute hot and cold spots, subtle asymmetries, are scrutinized to see if they carry whispers of a deeper pre-Big Bang history. Some researchers have even claimed that circular patterns in the microwave sky could be echoes of past universes that collapsed before ours began. These claims are controversial, disputed fiercely, but they highlight the hunger to glimpse beyond our cosmic birth. Large-scale surveys of galaxies also provide a kind of fossil record. The way galaxies cluster, the voids that stretch between them, the filaments that weave them together, all encode information about the universe's early conditions. If the cosmos had no beginning, if it emerged from cycles or from eternal inflation, then perhaps the imprint of those processes still lingers in this grand architecture. The Sloan Digital Sky Survey, the Dark Energy Survey, and the upcoming Euclid mission and Vera C. Rubin Observatory are mapping these structures with unprecedented precision, seeking patterns that no single finite beginning could explain. But perhaps the most tantalizing observations come not from what we see, but from what we do not. If the universe is eternal, then black holes may play a role as cosmic engines, recycling matter and energy across cycles. In some scenarios, black holes could even seed new universes, each one budding off from the singularities that lie at their hearts. Detecting such processes directly may be beyond us, but gravitational wave astronomy, the new science of listening to ripples in space-time, may someday provide hints. The collisions of black holes, the tremors of the early universe, could reveal whether our cosmos is truly one of many or a lone creation. Another clue lies in the mystery of cosmic inflation. If inflation was eternal, then the sky may reveal scars from bubble universes colliding with ours. These would appear as strange anomalies in the CMB, cold or hot regions that break the otherwise smooth pattern. Scientists have searched for them, and while no definitive evidence has been found, the possibility remains alive. If such scars were discovered, they would be nothing less than signs of other universes, proof that eternity exists not as abstraction, but as observable fact. We must also consider the role of entropy, the measure of disorder in the universe. The second law of thermodynamics states that entropy increases with time. If the universe is eternal, why has it not already reached a state of maximum entropy, a heat death, where no energy remains to fuel stars and galaxies? This is one of the sharpest challenges to an eternal cosmos. To resolve it, physicists propose mechanisms by which entropy might reset or be recycled. In bouncing models, entropy could be diluted or shed into dimensions beyond our own. In eternal inflation, new universes constantly form with low entropy, allowing local beginnings within a larger eternal framework. Observations of entropy distribution in cosmic structures may one day illuminate which of these pictures is true. Dark energy, too, complicates the story. This mysterious force, discovered in the late 1990s, is driving the accelerated expansion of the universe. In a finite Big Bang model, this expansion may eventually lead to a cold, dark eternity of isolation. But in eternal models, dark energy could play a different role, perhaps as the fuel for inflationary expansion, birthing new regions of space-time. If so, the very acceleration we observe today could be a clue that eternity is woven into the cosmos at its most fundamental level. The instruments humanity now builds are designed with such questions in mind. The James Webb Telescope peers farther back than any of its predecessors, looking for the first galaxies, the first stars, testing whether the timeline of cosmic dawn fits the Big Bang's predictions or hints at something older. The Event Horizon Telescope captures the shadows of black holes, probing the extremes of gravity where singularities and potential bridges to other universes might lurk. Even particle accelerators on Earth, smashing protons together at nearly the speed of light, are part of the search, attempting to recreate conditions close to the Big Bang and to uncover whether our laws of physics can naturally give rise to universes again and again. Every observation is a dialogue with eternity. The cosmos answers us not in words, but in faint light and subtle patterns, in whispers of radiation and the silent fall of galaxies. The steady-state theory may have been cast aside, but its spirit lives on in this relentless search for signs that the universe has no beginning. Our tools grow sharper, our reach grows longer, and with each new discovery, we learn whether the sky is telling a story with a first page or whether it is reading us a book without end. But as much as evidence guides us, there remains a deeper human tension. Eternity resists not only measurement, but imagination. To know that the universe has no beginning would alter how we see ourselves, our place in the vast order of things. Are we fleeting sparks in an endless cycle, or children of a singular creation? The answer shapes not just science, but philosophy, culture, even the meaning of existence. And so we look outward and inward at once. Our telescopes extend our sight. Our equations extend our thought. But the question lingers at the edge of comprehension. Has the universe always been here, waiting for us to notice? Or is what we see only one chapter in a book whose first words lie forever beyond our grasp? To speak of an eternal universe is to brush against the deepest currents of human thought, where science, philosophy, and culture converge. Long before the telescope, long before equations or laboratories, people stood under the night sky and wondered whether the stars had always been there. The idea of eternity is not new. It is ancient, woven into myths and religions, into poetry and philosophy. To contemplate a cosmos with no beginning is to ask questions not only of physics, but of meaning. In nearly every civilization, there are echoes of eternity. Hindu cosmology imagines vast cycles of creation and destruction called kalpas, where the universe is born, dies, and is reborn endlessly, with no ultimate start or finish. The Maya envisioned time as circular, great wheels turning forever, with ages repeating. The Stoic philosophers of Greece believed in ekpyrosis, a universe consumed in fire and born again in eternal recurrence. These visions, separated by continents and centuries, all grapple with the same unsettling thought, that time has no first moment and existence has no ultimate anchor. When science began to claim the heavens for itself, it too inherited this tension. Aristotle argued that the cosmos was eternal, without beginning or end, ungenerated and indestructible. His eternal universe was perfect and unchanging, a view that shaped Western thought for nearly 2 millennia. The Christian theologians who later wrestled with Aristotle were forced to defend the notion of creation in time, a beginning, a moment when God said, "Let there be light." Here lay not just a scientific or philosophical disagreement, but a cultural and spiritual divide. To deny a beginning was to challenge the very narrative of divine creation. To assert one was to place the cosmos firmly within a story with a first chapter. This divide echoes still in our modern discourse. The Big Bang, though born of mathematics and evidence, carries cultural weight as a moment of creation. The steady-state theory, though discarded by science, remains symbolically powerful as an alternative that resists beginnings. When Fred Hoyle dismissed the Big Bang, he was not only making a scientific argument, but a philosophical statement, that the universe does not require a birth and therefore does not invite questions of what or who lit the fuse. For many, the thought of an eternal universe is dizzying, even unsettling. We are beings of beginnings. Our lives start with birth, our days with sunrise, our stories with opening lines. A cosmos without such a boundary seems alien, unfathomable. Yet it also carries a strange comfort. If the universe is eternal, then we are part of something without end, something that has always existed and always will. Our mortality feels smaller against that backdrop, like waves upon a sea that never ceases. Philosophers have long debated whether eternity makes life meaningless or profoundly meaningful. If everything has already happened infinitely many times, as in some interpretations of eternal recurrence, then are our choices trivial, repetitions of cycles we cannot escape? Or does this repetition grant them a strange weight, as Nietzsche suggested, forcing us to live as though every act will echo forever? If the cosmos is eternal, then the patterns of life, birth, love, death, struggle, are not accidents of one moment, but features of existence itself. To embrace this is to see meaning not in singular origins, but in continuity. Art and literature have often reached for eternity, sometimes in awe, sometimes in fear. The poet William Blake saw infinity in a grain of sand, eternity in an hour, suggesting that the eternal was not only cosmic, but present in every moment. Jorge Luis Borges wrote stories of infinite libraries and endless books, metaphors for a reality without beginning or end. In music, composers like Wagner and Mahler sought to capture timelessness through cycles and unresolved chords. These works resonate with the same intuition as steady-state cosmology, that existence is not a line, but a circle, a sea, and endless flow. Culturally, the idea of eternity challenges how we understand history. Modern societies often imagine history as a line, primitive past, modern present, advanced future. But an eternal cosmos undermines this narrative. If the universe has no beginning, perhaps time is not progress, but process. Perhaps civilizations, like stars, rise and fall endlessly with no ultimate destination. This thought can be humbling. It suggests that our technological achievements, our dreams of exploration, even our survival as a species, are chapters in a book without end. But it can also be empowering, for it reminds us that we are participants in a story much larger than ourselves, one that does not depend on a final resolution. In personal terms, eternity confronts us with our own finitude. Against a backdrop of infinite time, a human life is unimaginably brief. The years of one person, the centuries of one civilization, vanish like sparks. Yet many find in this contrast a kind of liberation. If the cosmos has always been, then our smallness is not a flaw but a fact, and meaning must be sought not in scale but in experience. To know that the stars have burned for billions of years and may burn for billions more is to realize that our existence is both fragile and extraordinary. We are finite creatures in an infinite stage play, but that does not make our roles less significant. It makes them precious. The steady-state theory, though rejected, planted seeds that linger in culture. It suggested a cosmos that did not need a beginning, and by doing so, it reminded us that beginnings themselves may be illusions. Hoyle may have lost the scientific debate, but his resistance to origins continues to provoke thought in fields far beyond astrophysics. Philosophers, theologians, and artists still wrestle with the same question. If the universe is eternal, what does it mean to live in it? Perhaps the truest challenge is not scientific, but existential. Can we, creatures of time, accept timelessness? Can we imagine ourselves in a universe with no first breath and no last sigh? And if we can, does it change how we live our short, luminous lives? Standing under the night sky, it is easy to feel the weight of infinity pressing down. The stars we see are ancient. Some are already dead, their light only now reaching us. Galaxies wheel in silence across the void, unhurried by human clocks. Against such immensity, the idea of eternity no longer feels abstract. It is written in the sky itself, in patterns older than humanity, older than Earth, perhaps older than any beginning at all. And so the eternal universe is not only a theory, it is a mirror held up to our imagination, reflecting back both our fear of insignificance and our longing for permanence. Whether or not the cosmos truly has no beginning, the very act of asking forces us to expand our sense of meaning, to stretch our minds toward the infinite, and to see ourselves not just as creatures of time, but as part of eternity itself.
At the heart of the Big Bang model lies a troubling paradox, the singularity. When we trace the equations of general relativity backward in time, the expansion of the universe shrinks toward an infinitely dense point, a moment when all matter, energy, and even space itself are compressed into a state with no volume. At that singularity, the mathematics break down. Gravity becomes infinite. Temperature becomes infinite. Our physical laws simply stop working. In a sense, the singularity is less a description of reality than a confession of ignorance. It marks a boundary beyond which Einstein's equations cannot go. For decades, cosmologists have wrestled with this problem. If the singularity is real, then it seems to demand a beginning, a first instant in which the universe blinked into existence. But many suspect that the singularity is an illusion, a symptom of using incomplete mathematics. Just as Newton's laws of motion fail at speeds approaching light, general relativity may fail in the extreme densities of the early universe. What is needed is a deeper theory, one that unites gravity with quantum mechanics, a theory of quantum gravity. Quantum gravity remains one of the greatest quests in modern physics. Two leading candidates, string theory and loop quantum gravity, offer radically different pictures, but both share a crucial feature. They eliminate the singularity. Instead of a universe that begins from an infinitely small point, they propose that space and time themselves have a discrete quantum structure. Just as matter is made of atoms, space-time may be woven from tiny quanta, indivisible units that cannot be compressed beyond a certain scale. If so, the universe could never reach a true singularity. Instead, something else must happen at the edge of time. In loop quantum gravity, the Big Bang is replaced by a big bounce. As the universe contracts, the density rises. But when it reaches a critical threshold, quantum effects generate a repulsive force, countering gravity and preventing collapse into a singularity. The universe rebounds, expanding outward again. In this view, our Big Bang was not the beginning, but the moment of transition from a prior contracting universe. Time stretches endlessly in both directions. No first instant, no ultimate origin. Only cycles of collapse and expansion. String theory approaches the problem differently, imagining that the fundamental building blocks of reality are not particles, but vibrating strings, existing in multiple dimensions. In some string cosmologies, the Big Bang is not a creation event, but the result of higher dimensional brains colliding. Our universe may be one brain in a larger dimensional space, and the bang was the release of energy from a cosmic collision, an event that could happen again and again. The singularity is smoothed away by the mathematics of strings, replaced by a dynamic, eternal stage where universes can spark into being without ever requiring a true beginning. Both approaches suggest that the singularity is not a wall, but a doorway. What lies beyond may be other universes, other cycles, or even other forms of time. Some quantum cosmologists argue that near the Planck scale, the unimaginably small realm where quantum gravity rules, our ordinary concept of time ceases to apply.
Time as we know it may not be fundamental at all. It may emerge only at larger scales, a property of collective behavior, much like temperature emerges from the motion of molecules. If this is true, then asking what happened before the Big Bang may be meaningless in the same way as asking what is north of the North Pole. There was no before because before had no meaning. And yet, the rejection of a singular beginning does not automatically mean the universe is finite in age. It could mean that time existed in another form before the Big Bang, or that it stretches infinitely backward, hidden beneath the veil of quantum physics. In fact, some models suggest a pre-Big Bang universe with its own stars, galaxies, even civilizations, obliterated in the collapse, but leaving faint traces in the structure of our cosmos. These traces might linger as subtle imprints in the cosmic microwave background, or as exotic gravitational waves echoing through the fabric of space. If we could detect them, we might prove that the Big Bang was not the beginning at all, but merely the latest chapter in an infinite story. The singularity problem also forces us to rethink what we mean by creation. In the classical picture, the universe was created from nothing at a singular moment. In quantum cosmology, however, creation may be a continuous process. Particles can appear spontaneously from the quantum vacuum, borrowing energy briefly before annihilating. Extrapolated to the cosmos, perhaps universes themselves can emerge from the quantum vacuum, each one a fluctuation in an eternal backdrop. Our universe would not be unique, nor would it be privileged by having a beginning. It would simply be one fluctuation among countless others. This vision resonates strangely with Hoyle's steady-state universe. Where Hoyle imagined atoms of hydrogen continuously appearing to sustain the cosmos, quantum cosmology imagines entire universes appearing, sustained by the laws of physics themselves. Both views dissolve the need for an origin. Both replace beginnings with processes. Both suggest that existence itself is the natural state, not an anomaly in need of explanation. Still, these are bold speculations, not yet proven. Detecting evidence for quantum gravity is extraordinarily difficult. The Planck scale, where these effects dominate, is far beyond the reach of our particle accelerators. Instead, cosmologists search for indirect signs, patterns in the cosmic microwave background, the polarization of ancient light, the spectrum of gravitational waves. Each new telescope, each new detector, is a probe into the shadow of the singularity, an attempt to see whether time has a boundary or whether it stretches without limit. The singularity, then, is more than a mathematical curiosity. It is the fulcrum of the deepest question we can ask. Did the universe begin, or has it always been? To eliminate the singularity is to eliminate the need for a beginning. And to do that is to place eternity back on the table, not as myth, not as philosophy alone, but as physics. Imagine for a moment if the singularity truly vanishes under quantum gravity. Imagine if one day an observation confirms that our universe was born not from nothing, but from something before. The entire human story of origins would shift. The Big Bang would become not the moment of creation, but a transition in a universe that has always been here. That thought, unsettling and awe-inspiring, carries us back to the ancient question of eternity, now sharpened by the tools of modern physics. If the singularity problem hints that the universe may have no true beginning, then the mysteries of dark matter and dark energy deepen the enigma still further. They are the great unknowns of modern cosmology, forces that shape the cosmos on the largest scales, yet remain hidden from direct detection. Together, they account for about 95% of the universe, leaving ordinary matter, the stars and galaxies we see, as only a small fraction of reality. And if we wish to ask whether the universe might be eternal, then we must confront these invisible players, for they may hold the keys to cosmic destiny and possibly to cosmic eternity. Dark matter was the first of the two to announce its presence, though not directly. In the 1930s, astronomer Fritz Zwicky studied clusters of galaxies and noticed something strange. The galaxies moved too fast to be held together by the gravity of the visible matter alone. There had to be more mass than what could be seen, some unseen substance generating extra gravity. Later, in the 1970s, Vera Rubin confirmed this puzzle on galactic scales. Stars at the edges of galaxies orbited too quickly. The galaxies should have flown apart unless an invisible halo of mass was holding them together. That missing mass became known as dark matter. Though we cannot see it, dark matter reveals itself through gravity. It bends light through gravitational lensing. It influences the formation of galaxies. It sculpts the cosmic web of filaments and voids that stretches across the universe. And yet, after decades of searching, physicists still do not know what dark matter is. It might be exotic particles left over from the early universe, weakly interacting massive particles, or axions, or something stranger still. Or perhaps gravity itself behaves differently on cosmic scales, requiring a new theory of space-time. Whatever the answer, dark matter has shaped the universe from its earliest epochs, guiding the growth of structure from tiny fluctuations into the grand architecture we see today. Dark energy is even more mysterious and even more crucial for our question of eternity. In 1998, two teams studying distant supernovae made a shocking discovery. The expansion of the universe is accelerating. Instead of slowing under the pull of gravity, galaxies are flying apart faster and faster. To explain this, cosmologists invoked a new form of energy, dark energy, permeating space itself, driving expansion with a repulsive force. In Einstein's equations, it can be represented as a cosmological constant, a vacuum energy that remains constant as space expands. Or perhaps it is not constant at all, but a dynamic field, evolving with time, something stranger than we have yet imagined. This acceleration has profound implications for the fate of the universe. In a simple Big Bang model, without dark energy, the universe might expand forever, slowly coasting into heat death or collapse back into a big crunch. But with dark energy dominating, expansion accelerates without end. Galaxies recede beyond the horizon of visibility. Stars die, black holes evaporate, until the universe becomes cold, dark, and empty, a lonely eternity. But if dark energy is not constant, if it evolves, then stranger fates await. It could weaken, allowing gravity to pull the cosmos back into cycles of collapse and rebirth. Or it could strengthen, tearing even atoms apart in a big rip, an apocalyptic unraveling of space-time. Now, here is the crucial question. Can dark energy and dark matter allow for a universe with no beginning? The answer may lie in their behavior not only now, but across all cosmic time. If dark energy is truly constant, then perhaps inflation and expansion are two aspects of the same eternal process. The same energy that drives today's acceleration may have driven inflation at the dawn of our cosmos. In this picture, the universe could be part of a steady state of eternal inflation with dark energy as the fuel. Universes like ours bubble off endlessly, each beginning not from nothing, but from the energy of the vacuum itself. There is no first bubble, no last bubble, only an infinite froth. Dark matter, too, might play a role in sustaining cycles. If black holes are built from dark matter, or if dark matter has properties that allow it to persist across cycles of collapse and bounce, then it could act as the scaffolding of eternity, ensuring that structure always reemerges. Some theories even suggest that dark matter might be the ashes of previous universes, particles surviving across cycles, carrying information from one cosmic era to the next. If that is true, then eternity is not only possible, but observable. Somewhere in the fabric of dark matter could lie fossil traces of a time before our Big Bang. There are, of course, enormous challenges to such visions. We cannot detect dark matter directly. We do not know whether dark energy is constant or evolving. We have no clear evidence of cycles or of universes before our own. Yet the very existence of these mysteries keeps the question alive. If the universe is mostly composed of things we do not understand, then how can we declare with confidence that it had a beginning? Our ignorance is vast enough to allow for eternity. The pursuit of answers drives some of the most ambitious projects in science today. Deep underground, detectors filled with liquid xenon wait for the faintest whisper of dark matter particles. In space, satellites measure the distribution of galaxies, searching for the fingerprints of dark energy in their clustering. The James Webb Space Telescope peers into the earliest galaxies, testing whether their growth matches a universe with a definite beginning or hints at deeper cycles. Each experiment, each observation, is a step closer to understanding whether our cosmos has a finite age or infinite in scope. Philosophically, dark matter and dark energy remind us of humility. The universe we see, the stars and planets, the galaxies and nebula, accounts for less than 5% of what exists. The rest is hidden, unknown, possibly unknowable. To declare that the universe had a beginning is bold. To consider that it might be eternal is bold in another way. Both claims stretch our understanding. Both force us to confront the limits of knowledge. But perhaps the strangest thought of all is that dark matter and dark energy themselves may be eternal. Stars and galaxies come and go, atoms form and decay, but the invisible majority may endure forever, the silent background of reality. If so, then the universe may have no beginning because its true substance never began. It has always been here, in forms we are only now beginning to glimpse. And so, as we try to measure the unmeasurable, to detect the undetectable, we edge closer to the ultimate question. Perhaps eternity is not hidden in distant galaxies or in the first instance of time, but in the very fabric of what holds the cosmos together and drives it apart. Dark matter and dark energy may not only shape the universe, they may prove that it never began at all. Black holes are among the most terrifying and mysterious objects in the cosmos, yet they may also be the key to understanding whether the universe has a beginning or whether it is eternal. They sit at the crossroads of gravity, quantum mechanics, and cosmology, where our most powerful theories collide and, too often, fail. To peer into the nature of black holes is to glimpse both the end of things and, perhaps, the possibility of new beginnings that never truly start or end. A black hole forms when matter collapses under its own gravity beyond a critical threshold. Stars many times the mass of our Sun end their lives in supernova explosions, leaving behind dense remnants that can, if massive enough, collapse into black holes. In the centers of galaxies, supermassive black holes millions or billions of times the mass of the Sun lurk, shaping the dynamics of stars and fueling quasars with their immense gravitational pull. Black holes are objects of endings, swallowing matter and light, erasing information behind an event horizon from which nothing escapes. They are symbols of finality. And yet, paradoxically, some theories suggest they may also be engines of creation. When we look at a black hole closely, not directly, but through the mathematics of Einstein's equations and the hints of quantum physics, we find not only death, but a strange kind of rebirth.
At the heart of a black hole lies a singularity, a point where density and curvature become infinite, much like the supposed singularity of the Big Bang. But just as many physicists suspect the Big Bang singularity is not real, but an artifact of incomplete theory, so too might the singularity inside a black hole be resolved by quantum gravity. If so, the inside of a black hole may not be an end, but a transition. Some have speculated that each black hole could be a bridge, a doorway into another region of space-time, or even into a new universe altogether. This idea, radical as it sounds, arises naturally in some cosmological models. If a collapsing star avoids a singularity through quantum effects, its core might bounce into another universe, spawning a new cosmos with its own dimensions, space, and time. From our perspective, the black hole is a grave. From the perspective of that new cosmos, it is a cradle. This is sometimes called the fecund universes hypothesis, a vision of cosmological reproduction, in which universes give birth to universes through the collapse of matter into black holes. If this is true, then eternity takes on a new form. Our universe may not have had a single beginning, but instead may be part of an eternal lineage, a branching tree of universes, each budding from the black holes of its parent. The Big Bang itself might have been the interior of some colossal black hole in another universe, its event horizon hidden to us, but its collapse manifesting as our expansion. Beginnings and endings dissolve into cycles of transformation, where every death is also a birth. Even within our own universe, black holes refuse to remain silent. In the 1970s, Stephen Hawking discovered that they are not truly black, but glow faintly with thermal radiation due to quantum effects near the event horizon. This Hawking radiation means that black holes are not eternal prisons, but eventually evaporate, shrinking over unimaginable timescales until they vanish. But what becomes of the information they swallow? This information paradox is one of the deepest puzzles in physics. Some argue that the information is encoded in the radiation itself, smeared across the horizon like a cosmic hologram. Others suggest it may be preserved in subtle ways we do not yet understand. Still others hold that the information may seed new universes, carried into other dimensions through the black hole's hidden interior. If information is never destroyed, as quantum mechanics insists, then perhaps nothing ever truly ends. The atoms of our bodies, the light of our stars, the data of entire civilizations may not vanish into oblivion, but be recycled in forms beyond our comprehension. This idea aligns uncannily with the dream of an eternal cosmos. If black holes preserve, transform, and rebirth information, then the universe itself may be eternal in the most profound sense. Not a static, steady state, but a steady flow, an eternal conservation of existence across infinite transformations. Black holes also serve as laboratories for testing the boundaries of physics. Their intense gravity allows us to probe general relativity under extreme conditions, while their quantum behavior pushes us toward a theory of quantum gravity. The Event Horizon Telescope has already imaged the shadow of a black hole, offering a direct glimpse of the horizon itself. Gravitational wave detectors, like LIGO and Virgo, have listened to the collisions of black holes, ripples in space-time that reveal their dynamics. Each observation brings us closer to understanding whether black holes are simply dead ends or cosmic gateways. Consider the possibility that every black hole is a seed, and that each seed grows into a universe of its own. If true, then the cosmos may be an infinite forest of universes, branching endlessly, with no single beginning, no ultimate root. Each universe would contain its own laws of physics, its own galaxies and stars, perhaps its own beings pondering eternity.
Our universe may be just one branch, one leaf in an endless tree. The eternal is not a single static whole, but a living, growing structure, always changing, always renewing. Even if this vision proves too fanciful, black holes remain central to the question of eternity. They are the ultimate recyclers, swallowing matter and energy, perhaps even time itself, and returning them in forms we cannot yet predict. They remind us that endings may not be final, that what looks like annihilation may be transformation. In their silence and darkness, they may carry the loudest message of all, that the universe is deeper, stranger, and more enduring than any beginning or ending we can imagine. As we continue to study black holes, as new telescopes peer into their shadows and new detectors feel their tremors, we may find answers that reshape not only our theories, but our sense of existence itself. For in the heart of these cosmic abysses may lie the truth of whether the universe had a beginning, or whether it has always been, eternal and unending, reborn endlessly through the dark engines of creation we call black holes.
The multiverse is perhaps the boldest reimagining of the cosmos that modern science has ever produced. It challenges the very notion of the universe as a singular, all-encompassing reality, suggesting instead that what we see, our galaxies, our stars, our cosmic microwave background, is but one patch in a boundless mosaic. If this vision is true, then the question of whether the universe has a beginning may be misplaced. Our cosmos may have begun with the Big Bang, but the multiverse itself might be eternal, endlessly spawning new universes without ever needing a first one. The seeds of this idea were planted in the strange physics of cosmic inflation. In the early 1980s, Alan Guth, Andre Linde, and others developed inflationary theory to explain why the observable universe is so flat, so uniform, and so vast. Inflation proposed that in the first tiny fraction of a second after the Big Bang, space expanded exponentially, doubling in size again and again at a speed faster than light. This immense stretching smoothed out irregularities and set the initial conditions for the cosmos we inhabit. But inflation carries a surprising implication. In most versions of the theory, it never ends everywhere at once. While it stops in some regions, allowing universes like ours to form, it continues indefinitely in others, bubbling outward eternally. Each bubble becomes a universe, with its own Big Bang, its own laws of physics, its own stars and galaxies. And this process has no global beginning, no final end, just eternal creation. In this view, our universe is a single bubble in an infinite froth. The Big Bang we see was local, not universal. Beyond our cosmic horizon, beyond the edge of what we can observe, countless other universes expand and evolve, perhaps with properties so different from ours that we would scarcely recognize them as kin. Some may harbor life. Others may be sterile voids of radiation. Some may have stars that live for 1 trillion years. Others may collapse within moments of birth. The multiverse is not a single universe repeating forever, but an endless proliferation of diversity, a cosmic ocean without shore. For the question of eternity, the implications are profound. If the multiverse exists, then there was no single moment of creation. There may never have been a time zero. Instead, universes are always forming, always emerging from the inflating background. Our own cosmos might feel like it had a beginning 13.8 billion years ago, but that beginning is just one bloom on a tree that has been blossoming forever. Eternity is not stillness, but growth, an infinite branching of possibilities. Some physicists go further, suggesting that the laws of physics themselves might vary across universes. The constants that shape our cosmos, the strength of gravity, the charge of the electron, the speed of light,
might be different in others. This raises a curious thought. If there are infinitely many universes, then perhaps there is one for every possible variation. Some universes would be chaotic, unable to support complexity. Others, like ours, would permit stars, chemistry, life, and consciousness. In such a multiverse, we exist not because the universe was finely tuned for us, but because among infinite possibilities, there had to be universes where beings like us could emerge. We find ourselves in one of them simply because we are here to ask the question. This anthropic principle is controversial, but it provides one way to reconcile eternity with the uniqueness of our cosmos. But is the multiverse science or speculation? Critics argue that if other universes are forever beyond our observational reach, then they are metaphysical, not physical. Science, after all, demands evidence. And yet supporters counter that the multiverse is not conjured from imagination, but arises naturally from the mathematics of inflation, from the structure of string theory, from the puzzles of quantum mechanics. If our best theories point toward an eternal multiverse, then perhaps it is less speculative than refusing to follow where the equations lead. Evidence may still be possible. Some physicists search for scars of collisions between bubble universes, imprinted in the cosmic microwave background, faint asymmetries or anomalies that could betray a neighboring cosmos brushing against ours. Others look to high-energy physics, probing whether our laws of nature hint at deeper structures that only make sense in a multiverse. The search is difficult, perhaps impossible, but it is not abandoned. The allure of eternity demands it. The multiverse also reshapes how we think about beginnings in a more subtle way. Even if inflation itself had a start, even if the multiverse was born in some distant past, its endless generation of universes means that beginnings are relative. From inside any universe, there appears to be a starting point, a big bang, a moment when space and time ignite. But from the outside, from the eternal backdrop of the multiverse, there is no true origin, only an endless unfolding. What feels like a beginning to us is just a local flare in a process that never stops. This vision resonates with the old steady-state dream, though on an unimaginable scale. Hoyle imagined hydrogen atoms appearing to sustain an eternal universe. The multiverse imagines entire universes appearing endlessly, sustained by inflation. The principle is the same: continuity without origin, creation without beginning. The steady state was discarded, but its spirit lives on in the multiverse, reborn in mathematics far stranger than Hoyle could have imagined. For human thought, the implications are staggering. If the multiverse is real, then our universe is not the whole, but a single fragment. Our beginning is not the beginning. Our fate is not the end. Eternity stretches not in one line of time, but in infinite branches of possibility. The story of everything becomes not a single book, but an endless library, where every page is written and rewritten forever. Yet this raises another question. If the multiverse is eternal, what does that mean for us? Does it render our lives trivial, one of infinite repetitions across countless worlds? Or does it make them miraculous, the improbable spark of consciousness in one small corner of infinity? The answer may lie not in cosmology, but in how we choose to interpret it. Eternity can make us feel small, or it can remind us that our existence, however brief, is part of a grandeur beyond measure. The multiverse does not end the question of beginnings, it multiplies it. But it offers one clear possibility, that what we call the beginning of the universe was never the beginning of all things. The true universe, the multiverse, may have no beginning at all, only an eternal dance of creation without origin.
The idea of cycles has haunted human imagination for as long as we have looked at the heavens. Unlike the linear concept of time, a story with a beginning,
middle, and end, the cyclic vision sees time as a wheel, always turning, always returning. Day follows night, seasons follow each other, the moon waxes and wanes, and stars rise and set in predictable rhythms. For early cultures, the cycles of nature seem to mirror the cycles of existence itself. Why should the universe be any different? Perhaps all of reality is not a straight line, but a circle, endlessly repeating its stages. In ancient India, Hindu cosmology described the universe as undergoing infinite cycles of creation, preservation, and destruction, each cycle lasting billions of years. These cycles were not simply metaphor, but cosmic fact, embedded in the very structure of time. In Buddhism, too, the wheel of existence turns without beginning or end, and liberation comes only by stepping outside of it. The Maya conceived of world ages that rose and fell like suns, each destroyed and replaced by the next. The Stoics of Greece imagined ekpyrosis, a universe consumed in fire, only to rise again from its ashes in an eternal recurrence. The Norse envisioned Ragnarok, a cataclysm that destroyed the world, followed by renewal. Across cultures, across millennia, the cyclic universe was not the exception, but the rule. Even philosophy bent toward cycles. Friedrich Nietzsche famously declared the doctrine of eternal recurrence, the idea that every moment, every action, every life would repeat infinitely, played out again and again across endless time. For Nietzsche, this was not a scientific claim, but an existential challenge. If your life were to recur eternally, would you embrace it as it is, or despair at its repetition? The thought of eternal return was meant to shock us into confronting the value of existence. When modern science arose, it initially cast aside cycles for linear time. Newton's universe was eternal, yes, but static and changeless, not cyclic. With Einstein and the discovery of cosmic expansion, time suddenly had a direction, an arrow pointing outward from a beginning. The Big Bang Theory framed the universe as a story with a first act, an unfolding drama. But as physicists pushed the theory to its limits, cycles returned, not as myth, but as possible cosmological models. One of the earliest was Richard Tolman's oscillating universe, proposed in the 1930s. He imagined the cosmos expanding, then slowing under gravity, collapsing in a big crunch, only to rebound in a new Big Bang. Expansion, collapse, rebound, an eternal heartbeat of the cosmos. Tolman's model, however, ran into a problem with entropy. With each cycle, disorder increased, making subsequent cycles larger and longer. This implied that the cycles could not stretch infinitely into the past. There had to be a first one. Still, Tolman's vision was influential, sparking decades of thought about how to reconcile cycles with the laws of thermodynamics. In more recent times, the idea has returned in new guises. Loop quantum cosmology replaces singularities with bounces, allowing the universe to contract and expand without a beginning. The ekpyrotic model of string theory suggests that our universe is one of many branes in higher dimensions, colliding periodically and producing big bangs with each clash. In such scenarios, cycles are not merely metaphor, but mechanisms, written into the mathematics of fundamental physics. Eternal recurrence also resonates with the problem of the singularity. If the universe began with a singularity, then time has a boundary. But if each collapse is followed by a bounce, then no boundary exists. Time stretches backward forever through cycles. Each universe gives birth to the next, with no first parent in the chain. The cycles may not be identical. Entropy, quantum fluctuations, or variations in fundamental constants could make each one unique, but the process itself has no beginning.
From a philosophical perspective, cycles blur the line between beginning and eternity. A linear universe demands an origin, a moment when time began. A cyclic universe avoids the need for an origin by embedding beginnings in endings. Every Big Bang is both the start of a new cycle and the continuation of an eternal rhythm. In this way, cycles reconcile our need for beginnings with the possibility of eternity. The psychological impact of such a vision is complex. On the one hand, eternal recurrence can feel oppressive, trapping us in endless repetition. On the other, it can be liberating, dissolving the anxiety of endings. If the universe always renews, then nothing is truly lost. Death itself becomes transformation, a phase in a cycle that will always return. For some, this echoes the spiritual promise of rebirth. For others, it is a purely natural rhythm, grander than any one life. Evidence for cycles remains elusive. Observations of the cosmic microwave background are combed for traces of previous universes, subtle imprints, anomalies that might be echoes of earlier cycles. Some researchers claim to see hints, patterns in the sky, that cannot be explained by a single Big Bang. Others remain skeptical, cautioning that the data are ambiguous. The search continues, for if we could confirm even the faintest whisper of a prior universe, it would revolutionize our understanding of time. Cycles also force us to reconsider the fate of the universe. In a one-time Big Bang model dominated by dark energy, the cosmos expands forever into cold emptiness. But in a cyclic model, endings are beginnings. A big crunch becomes a Big Bang. Heat death becomes rebirth. The universe is not a one-way journey, but a wheel, forever turning in the dark. Of course, cycles do not resolve every mystery. What mechanism drives the bounce? How is entropy reset? Are the cycles truly eternal, or did they begin at some distant past? These questions remain open, but the very act of posing them reminds us that eternity may not mean an infinite straight line, but an infinite circle. To contemplate eternal recurrence is to confront ourselves. If the universe cycles forever, then everything we do may return in some form, echoing across countless ages. Whether we find that terrifying or inspiring reveals much about how we see existence. For science, cycles offer a way to dissolve the singularity and avoid beginnings. For philosophy, they challenge us to live as if our choices matter eternally. For culture, they connect us with the oldest human intuitions, the vision of the cosmos as a wheel turning forever in the dark. And so, the idea of cycles remains one of the most haunting answers to the question of eternity. It is not linear, not finite, not bound by a first cause. It is rhythm, recurrence, eternal return. If true, the universe has no beginning, because every beginning is an ending, and every ending a beginning, forever.
Time, as we experience it, feels like an unstoppable current flowing in a single direction. We remember the past but not the future. We grow older but never younger. Stars burn their fuel and never rekindle themselves spontaneously. This sense of direction, the arrow of time, seems so fundamental that we rarely question it. And yet, in physics, time is a far stranger concept than our daily experience suggests. At the most basic level, the laws of physics do not actually prefer one direction over the other. The equations that describe particles and forces, whether in Newtonian mechanics, Einstein's relativity, or quantum theory, are symmetrical with respect to time. They allow processes to run forward or backward equally well. If a billiard ball can roll to the left, it can also roll to the right. If two atoms can collide, they can just as easily be imagined to uncollide in the math. So why, in reality, does time feel like a one-way journey? The answer lies in entropy, the measure of disorder. The second law of thermodynamics states that entropy in a closed system tends to increase. A glass shatters but never spontaneously reassembles itself. Heat flows from hot to cold, not the reverse. Order dissolves into disorder, giving time its irreversibility. In this sense, the arrow of time is thermodynamic, born from the relentless increase of entropy in the universe. Without it, there would be no distinction between past and future, no flow of time as we know it. But what does this mean for eternity? If entropy must always increase, then the universe cannot be eternal in any simple sense. It would have long ago reached a state of maximum entropy, a uniform, featureless expanse where no stars shine and no structures exist. Yet here we are, living in a universe filled with galaxies, stars, and complexity. This apparent contradiction suggests that either the universe did have a beginning in a low entropy state, the Big Bang, or that there is some mechanism by which entropy is reset or circumvented, allowing eternity without heat death. This is one of the most profound puzzles in cosmology. The Big Bang model begins with an extraordinarily low entropy state, far lower than what would be expected if the universe were eternal and randomly configured. Why did the cosmos start in such an improbable condition? Was this simply chance, or is there a deeper principle at work? Some physicists suspect that our understanding of entropy itself may need revision when applied to the entire universe. Others suggest that the universe may be much larger than what we see, with entropy balanced across regions in ways we cannot observe. In cyclical models, entropy poses a special challenge. If each cycle adds more entropy, then the cycles cannot stretch infinitely backward. There must have been a first one. To preserve eternity, cyclical cosmologies must find ways to eliminate or dilute entropy. Some theories propose that entropy is expelled into other dimensions during the bounce. Others argue that as the universe expands, entropy becomes diluted so that each cycle begins anew. In these scenarios, the arrow of time may itself reset with each cycle, creating a cosmos where eternity is possible because time itself is reborn endlessly. The arrow of time also raises a deeper question. Is time fundamental at all? Some physicists argue that time may be emergent, not basic. Just as temperature is not a property of individual molecules, but of collections of them, time may emerge from the statistical behavior of quantum states. If so, the flow of time is a large-scale illusion, born from entropy and information, not from the foundations of reality. In such a picture, eternity takes on a strange new meaning. The underlying reality may be timeless, while what we experience as time is a kind of emergent phenomenon. The universe may not need a beginning, because fundamentally it does not flow at all. It simply exists. Still, we cannot escape the experiential power of time's arrow. Our lives are bound to it. Stars burn because nuclear reactions move forward, not backward. Galaxies evolve because gravity pulls matter together, not apart. Civilizations rise and fall because cause precedes effect. The arrow of time is written into everything we know. If eternity exists, it must account for this arrow, either by stretching it infinitely backward, by cycling it endlessly, or by dissolving it into a deeper timeless framework. There are even speculative ideas that challenge the uniqueness of our arrow. Some cosmologists suggest that time's arrow might reverse in distant regions of the multiverse. If inflation spawns countless universes, then some may expand with entropy increasing, as ours does, while others contract with entropy decreasing relative to us. In those universes, beings like us, if they exist, would perceive time flowing forward from their perspective, though to us it would look reversed. Eternity then might be filled with countless arrows of time, each pointing differently, each local and relative. On the largest scales, the arrow of time may even connect to the fate of the cosmos. If entropy must always increase, then the universe seems destined for heat death. Stars will exhaust their fuel, black holes will evaporate, and matter will decay into a cold, thin mist of radiation. In that ultimate stillness, time itself may lose meaning, for without change, what is there to measure? But if cycles or multiverse processes renew entropy, then eternity avoids this fate. Time never ends because it never really runs down. It is always reset, always reborn, always local to each universe. And this brings us to the paradox at the heart of eternity. Time is both the measure of change and the substance of our experience. To imagine eternity without time is to imagine existence without sequence, without cause, without becoming, an existence utterly alien to human thought. But to imagine eternity with time, we must confront entropy, which seems to forbid infinite extension without change. Somewhere between these poles lies the truth. Perhaps time as we know it is not eternal, but eternity itself is timeless, a background in which universes and arrows of time come and go. For us, the arrow of time is an unbroken reminder of finitude. We grow old. We cannot return to the past. We live in one direction only. And yet, in contemplating eternity, we glimpse the possibility that time itself may be only a feature of our universe, not of existence as a whole. If so, then the universe may have no beginning, not because time stretches forever backward, but because beyond time lies something deeper, something eternal, in which beginnings and endings are illusions. The arrow of time drives us forward, but the question of eternity forces us to look beyond entropy, beyond heat death, beyond even time itself. To ask whether the universe had a beginning is to ask whether the arrow of time is absolute, or whether it is just one arrow among many in an eternal sky.
When we gaze into the night sky, we are not looking into space alone, we are looking into time. The light from distant stars and galaxies has traveled across billions of years to reach us, carrying with it the memory of what the cosmos looked like in ages past. The farther we look, the further back in time we see. But even this cosmic vision has a limit, the horizon of the observable universe. Beyond it, light has not had enough time to reach us since the Big Bang. This horizon is both our window into the past and a curtain that conceals the greater reality beyond. And behind that curtain may lie the answer to our deepest question. Does the universe have a beginning, or is it eternal? The observable universe is about 93 billion light-years across, though the universe itself is much larger, perhaps infinitely so. The reason for this discrepancy is the expansion of space. While the universe is 13.8 billion years old, the galaxies we see at the edge of our vision are far more distant than 13.8 billion light-years, because space has been stretching between us and them during the time their light has traveled. What we see is not a cosmic boundary, but a horizon, much like the horizon at sea, the limit of vision, not the edge of reality. Beyond it, galaxies continue, perhaps without end. This horizon is crucial for the question of beginnings. Everything we know about the universe's history comes from what we can observe within this bubble of light. The cosmic microwave background shows us the infant universe, but not what came before. The distribution of galaxies reveals billions of years of structure formation, but not the ultimate origin. We are like sailors on a vast ocean, able to see only to the horizon, unable to know whether the sea ends just beyond sight or stretches forever. And yet, cosmologists attempt to peer beyond, using indirect clues. For instance, the cosmic microwave background is almost uniform, with only tiny fluctuations. Why should regions of the sky so far apart, regions that could never have communicated at the speed of light, look nearly identical? Inflation provides an answer. A period of exponential expansion stretched a tiny patch of uniform space to cosmic proportions.
But inflation also raises the possibility of eternity. If inflation happened once, why not forever? Perhaps what lies beyond our horizon is not simply more of the same, but other universes, endlessly budding from an inflating background. In that case, our observable bubble is just one part of a far larger, eternal multiverse. The horizon also obscures the fate of the universe. If space continues expanding forever, galaxies beyond a certain distance will recede faster than light and vanish from view. Already, most galaxies are beyond reach. They may shine forever, but their light will never again arrive. In the distant future, even the nearest galaxies beyond our local group will disappear over the horizon, leaving future observers with the illusion that the universe is empty and static. The horizon shapes not only what we can see, but what we can know. It hides eternity, or its absence, behind a veil of light that will never reach us. Yet scientists are ingenious in their attempts to read the invisible. Gravitational waves, ripples in space-time itself, may carry information from before the cosmic microwave background, from epochs currently hidden to light. If detected, they could provide a glimpse beyond the horizon of our observable history, perhaps revealing evidence of a bounce, a prior universe, or other cosmic cycles. Similarly, subtle imprints in the polarization of the cosmic microwave background may betray processes from before the Big Bang, allowing us to peek past the supposed beginning. These are delicate, difficult measurements, but they are the closest we may come to looking beyond the curtain. There is also the question of the ultimate horizon, the cosmic event horizon created by dark energy. As the universe's expansion accelerates, more and more regions of space recede beyond the limit of causality. No signal, not even light, can ever cross that horizon to reach us. In a sense, we are trapped within a shrinking island of visibility, surrounded by an eternal ocean we can never touch. This cosmic isolation mirrors the human condition, finite beings in an infinite unknown. It also underscores the possibility that eternity exists, but forever beyond our direct observation. Philosophically, the horizon forces humility. It reminds us that our knowledge is partial, bounded, contingent. We cannot see the whole, we can only infer. The steady-state theory faltered because observations within our horizon contradicted it. But what lies beyond may still harbor processes akin to Hoyle's dream of eternity. Inflation and multiverse models suggest that what we observe is a small part of a grander whole, perhaps eternal, perhaps infinite. But because we are confined within our horizon, we may never know for certain. This limitation does not weaken the pursuit, it intensifies it. Human beings are creatures who push against boundaries. The horizon is a challenge, daring us to invent new instruments, new theories, new ways of seeing. Each generation extends the reach of observation. Galileo's telescope revealed moons of Jupiter. Hubble's telescope unveiled galaxies beyond our own. Webb's telescope now peers into the first billion years of cosmic history. Each advance brings us closer to the horizon, though never beyond it, and each reveals that the universe is larger, older, stranger than we imagined. But the ultimate question remains unanswered. Does what lies beyond the horizon confirm a beginning, or does it stretch backward into eternity? Perhaps the observable universe is just a small patch of an infinite cosmos that has always existed. Or perhaps it is one bubble in an eternal multiverse, with no first universe at all. Or perhaps beyond the horizon, time itself takes on forms we cannot conceive, dissolving the very distinction between beginning and eternity. For now, we stand at the edge of vision, gazing into a cosmic ocean whose shores we cannot see. The horizon is not the end, but the beginning of wonder. Beyond it may lie the truth of eternity, forever hidden, forever beckoning. If the universe truly has no beginning, then humanity's place within it takes on an entirely new dimension. We are accustomed to thinking of ourselves as children of a singular event, the Big Bang. In that narrative, everything has a timeline. Stars ignite, galaxies form, life evolves, civilizations rise and fall, all set within a cosmic history that stretches back 13.8 billion years to a unique origin. But if there was no beginning, if the cosmos has always existed in some form, then our story becomes something very different. We are not the result of a one-time genesis, but participants in an eternal process, a flicker in a rhythm that has no first beat. For some, this thought is unsettling. It strips away the notion of ultimate origin, a moment when existence itself began, a foundation upon which everything else rests. Without that foundation, we seem to drift in a sea without shore or anchor. Yet for others, eternity offers a deeper comfort. If the cosmos has always been, then our existence is not precarious but inevitable, part of an unbroken continuity that stretches without end. We are not latecomers to a story that began long ago. We are co-authors in a story that never began at all. This perspective reshapes our understanding of survival and destiny. In a finite universe, humanity's fate seems bound to a tragic arc. Stars will burn out, galaxies will fade, entropy will march toward heat death. In billions or trillions of years, the cosmos will grow dark, and whatever remains of us will be extinguished with it. But in an eternal universe, endings are never final. If time is cyclic, then after collapse comes rebirth, and after death comes renewal. If the multiverse is real, then somewhere in another bubble, beings like us may rise again, endlessly, without need for a first origin. Humanity's role in such a cosmos is not to defy endings, but to recognize that endings themselves may be illusions. Still, the eternal universe does not grant us immortality. Our species, our planet, even our galaxy may vanish, as countless others have before. But eternity reframes that impermanence. We are not fragile sparks against a finite darkness, but expressions of reality that has always produced sparks and always will. In a universe with no beginning, the emergence of life is not a singular miracle, but a recurring theme. Consciousness is not an anomaly, but a possibility woven into the fabric of eternity. If it happened here, it may have happened countless times before, and will happen countless times again. This vision also transforms our search for meaning. If everything is eternal, then the ultimate purpose may not lie in origins or endings, but in participation. Our lives matter not because they are unique in the vastness of time, but because they are part of an endless dance. Meaning is not diminished by eternity, but expanded. To live is to embody the eternal in a fleeting form, to carry forward the rhythm of existence for as long as we can. Yet eternity also poses a challenge. If everything repeats, if cycles stretch forever, then what distinguishes our actions? Are we condemned to play the same roles endlessly? Nietzsche's doctrine of eternal recurrence, though philosophical rather than scientific, presses on this anxiety. If you had to live your life exactly as it is, over and over for eternity, would you embrace it? The thought forces us to confront the weight of existence, to live as though each moment reverberates forever. If the universe is eternal, perhaps so too are the consequences of our choices. From a practical standpoint, eternity changes how we might approach the future. In a finite cosmos, survival feels like a desperate race against inevitable extinction. In an eternal cosmos, survival becomes participation in a process that will outlast any one civilization.
Our task is not to defeat entropy, but to align ourselves with the rhythms of renewal, to find ways of persisting across cycles or across universes. Colonizing space, spreading life beyond Earth, may not be a way of escaping an end, but a way of joining the eternal flow, ensuring that life remains one of the recurring notes in the cosmic symphony. There is also a spiritual dimension. For millennia, religions have promised eternity, whether through immortal souls, reincarnation, or divine creation. An eternal universe echoes these promises, though in a profoundly naturalistic way. Here, eternity is not bestowed by gods, but by physics, not a heaven outside time, but time itself without limit. In such a vision, humanity's longing for permanence finds fulfillment not in escape from the cosmos, but in recognition that we are woven into its eternal fabric. Of course, eternity also humbles us. If the universe has no beginning, then our age, 13.8 billion years since the Big Bang, is not the age of everything, but only the age of our bubble, our cycle, our local chapter. Countless others may exist beyond our horizon, older, younger, stranger. We are not central, not special, not the first nor the last. We are one of many expressions of an eternal cosmos. This humility can feel diminishing, but it can also be liberating. To be part of eternity is to belong to something infinite, something larger than any individual or species. The practical pursuit of science reflects this duality. Our telescopes and detectors, our theories and equations are all attempts to peer into eternity from our brief vantage point. We may never know for certain whether the universe had a beginning or not. Our horizon may always limit us, but in the act of searching, in the drive to ask, we enact the very spirit of eternity. Our curiosity, like the stars, is part of the eternal process. If the universe has no beginning, then humanity is not an accident of one singular event, but a natural flowering of reality itself. Our existence is one more chapter in a story that has no first page, no last page, only endless writing. In that vision, we find both humility and meaning. We are finite beings in an infinite cosmos. We are temporary, but part of what is eternal. And perhaps this is the true gift of eternity, not certainty, but perspective. To see ourselves as part of an unbroken whole, to live knowing that beginnings and endings are not absolutes, but illusions. To act as though our choices matter eternally, because in some sense they do. In an eternal universe, everything leaves a trace, everything participates, everything belongs. So humanity stands at a threshold. We can live as though we are fleeting sparks in a fragile cosmos, or as though we are participants in eternity. Science cannot yet tell us which vision is correct, but in choosing how to live, we shape our place in the eternal story. Imagine the Earth, a fragile blue world adrift in the vast dark ocean of the cosmos. Our ancestors once looked up at the stars and sought a beginning, a first spark that would explain why the heavens exist at all. Today we gaze with telescopes that can see back almost to the dawn of time itself, and yet the question remains unresolved. Did the universe begin in a singular moment of creation, or has it always been here, eternal, with no true first page? Science, philosophy, and human imagination have circled this mystery for centuries. The Big Bang provides a powerful narrative, a hot, dense beginning, expanding and cooling into the galaxies we see today. Its evidence is overwhelming: the cosmic microwave background, the abundance of light elements, the redshift of galaxies. And yet it leaves us with the singularity, a boundary where physics collapses, and the haunting question of what came before. To some, this means there was no before, that time itself was born in that instant. To others, it is a sign that our theories are incomplete, that the true story stretches further back into eternity.
The steady-state theory of Hoyle, Bondi, and Gold is gone as a scientific model, defeated by evidence, but its spirit survives in new forms. Eternal inflation, cyclic universes, quantum bounces, multiverses, all these theories echo the dream of an eternal cosmos, one that has no beginning and no end. Each proposes that the Big Bang was not the birth of everything, but only a transition, one event in a far greater story. The consequences of this vision are profound. If the universe has no beginning, then the meaning of existence changes. Our lives, our civilizations, even our planet are not fragile accidents of a singular origin, but expressions of an eternal process that has always unfolded and will always unfold. We are finite, yes, but part of something infinite. We are brief, but linked to rhythms that stretch without end. The fate of Earth, like all worlds, is sealed by cosmic processes. In a few billion years, the sun will exhaust its fuel, swelling into a red giant, consuming or scorching our planet. Humanity, if it survives, will be forced to seek new homes among the stars. Galaxies will drift apart as the expansion of space accelerates. Stars will die, black holes will evaporate, and our local universe may fade into darkness. But if the universe is eternal, then this is not the end. Perhaps new universes will be born from black holes. Perhaps time itself will cycle back, igniting a new Big Bang. Perhaps in the endless froth of the multiverse, countless new realities will bloom, each carrying echoes of what came before. And in those echoes, perhaps life will rise again. Perhaps beings in some distant epoch, on some distant world, will look up at their own night sky and ask the same question: did the universe have a beginning? And like us, they will wrestle with the mystery of eternity, torn between the comfort of origins and the awe of the infinite. For humans, the eternal universe is both a scientific hypothesis and a mirror for our deepest longings. We seek permanence in a world that constantly changes. We fear endings, and so we dream of eternity. But perhaps eternity is not a dream at all. Perhaps it is the truth of the cosmos, written into its very fabric. Not eternity as a static perfection, but as an endless process. Creation, destruction, renewal, again and again, without first cause and without final conclusion. Stand once more beneath the night sky. The stars shine as they did for our ancestors, as they will for those who come after us, each one a fire burning in the endless dark. If the universe has no beginning, then those stars are not the children of a singular creation, but part of an eternal flame that has always burned. To look at them is to look into infinity, to glimpse the eternal canvas upon which all existence is painted. Perhaps the true answer to the question of beginnings is not one that science alone can provide. Perhaps it lies at the intersection of physics, philosophy, and human imagination. What we know today is only a fragment of what eternity holds. But in asking, in searching, in daring to wonder whether the universe has no beginning, we touch the infinite. And in that touch, there is a kind of immortality. For though our lives are brief, though our world is fragile, our minds reach across the void to eternity itself. We are finite beings, but we carry the capacity to imagine the infinite, and that too is a form of eternity. The universe may not have begun. It may not end. It may be eternal, a boundless sea without shore. And we, small as we are part of it, woven into its endless story, luminous threads in a tapestry without first stitch and without last.